Hi everyone, my name is Voon. I'm a postdoc at ANU, and today I would like to introduce a new generation seismic array which uses fiber optics, and this is called distributed acoustic sensing, or in short, DAS. And first of all, I would like to thank AuScope for investing in the DAS technology for geophysical studies. And I would like to also introduce the group that's involved in this DAS project. Our lead CI, Professor Megan Miller, and collaborators, Professor Brian Kennett and Dr. Herb McQueen. So what is DAS? So DAS measures the optical properties of backscatter light to detect dynamic strain that happens along the fiber. So what does it do is that when you connect the DAS interrogator to a single fiber, it sends laser pulses along the fiber, and because fibers have imperfection, as the laser pulse hits the imperfection, it generates Rayleigh scattering and sends backscatter light all the way to the interrogator. And as seismic waves that come from earthquakes, oceans, or traffic passes across the fiber stretches or compresses ever so slightly, and this changes the optical properties of the backscattered light, and that translates into dynamic strain. And thus is considered as a distributed sensor because just one interrogator, one instrument can transform a continuous fiber optics into thousands of sensors measuring at the same time. And with this capability of distributed sensing, DAS is able to record seismic wavefield at a very high spatial temporal resolution. And the ability to record at high resolution is very important for imaging and also understanding seismic source. And in the past decade, there's many new instruments that allows very dense deployment. And one of it was the best example out there was the Long Beach nodal array. It's there are 5,200 coffee tin sized nodes placed at 100-meter spacing, which is shown as little dots on the map here. And as a regional events happen and the seismic wave crosses the array, we could see the wave front with the different polarity marked in two different colors crosses the array, and there's distortion to the wave front due to the structures of the under the array, and the structures could be faults, but we could see that there's a major disruption where the polarity flipped, and this is due to a unmapped fault in the region. And this type of deployment takes tremendous effort, 6 months with lots of manpower. And here I show a DAS array, which is also capable of recording the wave at very high resolution. So here is done on the submarine array, a submarine fiber, 20 kilometers long, that equals to 10,000 sensors at 2-meter spacing. And the regional event is also recorded on this array. And this is sensors on the x-axis, and we see the different wavefront arrives, a P, little p, big P. And then we can see that among these main arrivals, there's all this small scattering, and this is due to faults that was not known at that time. And this deployment is relatively simple with significantly less manpower, and also took less amount of time. And this deployment was 4 days long. And with the number of sensors in DAS array at very dense spacing, there are many potential to use DAS to improve our ability to, for example, detect seismic source. So here is an example at the Brady geothermal field in Nevada, where the fiber is laid out in zigzag manner in blue. And because it's a geothermal field, there are lots of seismic activity. And there are, here on the right shows the different events that was recorded. On the top right here is an event that has very high signal to noise ratio. So it can be visually identified. But then even though for the bottom two, these events are very hard to identify visually because of the poor signal to noise ratio, but the signals are coherent across the stations. So when they stack, these are still visible, and we can detect these events as a result. Another potential for DAS is for near surface imaging and monitoring. It's a small station spacing allows us to detect short wavelength structures. Here is an example of using dark fiber. So it's an unused telecommunication cable, 20 kilometer long, 2-meter spacing. And with the 2-meter spacing, they could do imaging at less than 100-meter depth, which is very important for detecting structures like VS30 or water table. And these measurements can be done continuously for years. So here's a 1.5-year deployment. And then with that, they could measure the seismic velocity change and try to understand it with reference to the change in hydrology. With the abundance of dark fibers in urban areas and across cities, there are many potential places and also applications to deploy DAS, but there are also some key challenges that we need to address. And one of the main ones was that DAS measures strength and not ground velocity, unlike a seismometer. So there is a different and strong azimuthal dependency, as DAS is most sensitive to signals along the fibers or axial direction. And here's an example of VibroSeis as an active source truck sending seismic waves across an array. And the arrays, which is in line with the signal, has very strong amplitude, and then the arrays that has changed geometry has very weak amplitude. Another challenge with DAS is that the fiber to ground coupling sometimes is not known, especially for dark fiber where the fiber has already been installed. And this is particularly important for amplitude-based studies. And last but not least, DAS experiment generates a huge data volume in orders of terabyte. Here, example of just a handful of experiments have generated cumulatively 800 terabyte. And this requires different thinking on how to efficiently process these data sets. With those in mind, we have a try in deploying a DAS in collaboration with the NASA Deep Space Network in Canberra. So it's a 6 weeks deployment on one of their unused dark fiber. And it's a 2-kilometer long fiber in a cased conduit trench 2-meter deep. And this array is complemented with 4 seismometers. And here are some pictures of us deploying the DAS array. So this is the interrogator installed on the server rack, which is about to be connected to the fiber optic cable in the yellow. And here is some of us doing tap tests, trying to physically locate the fiber and relate it to a latitude and longitude. And here's a picture of us deploying and calibrating the seismometer, which is buried in the ground. And this DAS data set is a little bit noisy, but then with a bit of pre-processing, we can identify several types of signal. So the one shown here is a quarry blast in Canberra that records as 1.2 local magnitude, shows up at the 50-second mark here. The other one, which is more interesting, which is a regional event 150 kilometers away at Jindabyne, where we can see clear P&S wave arrivals. And we note that this amplitude changes across the array by the changing in the color of intensity. And this, we find that it correlates with the change in the array geometry that's marked in little red dots. And some of the things that we're trying to do here is not only just to develop better ways in processing DAS data set, but also develop waveform modeling tools to model the amplitude and accounting for the ground coupling and the directivity effect. So here in the picture, we show simulations, so synthetic results, just accounting for the directivity effect. And we compare it to the observation and realize that there's a section where the observed strain rate is really weak. And we think this is related to the very poor ground coupling. And there's many more works to be done, but hopefully here I've shown that DAS has a lot of potential for seismic source detection and near surface imaging. And to really optimize DAS for dark fiber arrays, there are many key challenges that we need to solve. And there are more DAS array deployments in plan, and I will always welcome for new collaboration and new application for DAS. With that, thank you for listening.